Welcome to this Kotlin Best Practices tutorial on memory management and understanding garbage collection. In modern programming, managing memory efficiently is crucial for building high-performance applications. Throughout this video, we'll explore how Kotlin handles memory automatically, what garbage collection is, and the best practices to write memory-efficient code. Let's get started. Garbage collection is an automatic memory management process. It works by identifying and reclaiming memory that's occupied by objects which are no longer reachable or in use by your application. Instead of manually freeing memory like in languages such as C or C++, the garbage collector does this work for you automatically. This prevents common memory-related bugs like memory leaks and dangling pointers, allowing developers to focus on writing features rather than managing memory. Kotlin runs on two main platforms, each with its own memory management approach. When using Kotlin on the JVM platform, your code relies on Java's mature and sophisticated garbage collector for automatic memory management. This means you benefit from decades of optimization in the Java virtual machine. On the other hand, Kotlin Native, which compiles to native binaries, uses its own memory manager with a built-in garbage collector. Both approaches handle memory automatically, but understanding which platform you're targeting helps you write more efficient code. Memory in Kotlin applications is divided into two main regions, the stack and the heap. The stack stores primitive values, local variables, and method references. It's fast, and memory is automatically cleaned up when a method returns. The heap, on the other hand, stores objects and arrays. Allocation on the heap is slower, and this is where garbage collection comes into play. The heap is shared across all threads in your application, which makes it powerful, but also means it requires careful management through garbage collection. Let's walk through the life cycle of an object in memory. First, when you create a new object, it's allocated space on the heap. Second, as long as there are references pointing to that object from your code, it remains reachable and in use. The garbage collector knows not to touch it. Finally, when no more references exist to that object, it becomes unreachable. At this point, the garbage collector identifies it as garbage and reclaims its memory, making that space available for new objects. This cycle happens automatically throughout your application's runtime. Garbage collectors use reachability analysis to determine which objects can be safely removed. This process starts with GC roots, which are starting points like active threads, static fields, local variables, and JNI references. During the mark phase, the garbage collector traverses the object graph from these roots, marking all objects that can be reached. Then, in the sweep phase, it reclaims memory from all unmarked objects, those that are no longer reachable. This mark and sweep approach ensures that only truly unused objects are removed from memory. Even with automatic garbage collection, several memory issues can still occur. Memory leaks happen when objects remain referenced even though they're no longer needed, preventing the garbage collector from reclaiming that memory. Out-of-memory errors occur when the heap is exhausted and there's no space for new allocations. GC overhead refers to excessive garbage collection activity that consumes too much CPU time and degrades performance. Finally, reference cycles, where objects reference each other in a loop, need to be properly detected and handled by the garbage collector. Understanding these issues helps you write more robust applications. Let's look at practical ways to avoid memory leaks in Kotlin. A common mistake is setting an on-click listener on a button, but never removing it. This keeps the listener and potentially large objects in memory. The good approach is to explicitly set the listener to null in your onDestroy method. An even better solution is to use weak references, which allow the garbage collector to reclaim objects even if the weak reference still exists. Weak references are particularly useful for callbacks and listeners, where you don't want to prevent garbage collection. Object pooling is a powerful technique to reduce garbage collection pressure. The idea is to reuse objects instead of constantly creating and destroying them. In this example, we create an object pool class that maintains a list of reusable objects. When you need an object, you acquire it from the pool. If the pool has an available object, it returns it. Otherwise, it creates a new one. When you're done with the object, you release it back to the pool instead of letting it be garbage collected. This pattern is especially useful for frequently created objects like network requests, database connections, or temporary buffers. Let's recap the key points. First, garbage collection automatically manages heap memory by reclaiming unreachable objects, freeing you from manual memory management. Second, understanding the difference between stack and heap allocation helps you write more efficient code. Third, avoid memory leaks by properly removing listeners and using weak references when appropriate. Finally, reduce garbage collection pressure through strategies like object pooling and object reuse. By following these practices, you'll write Kotlin applications that are both memory efficient and performant. Thank you for watching and happy coding.
If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.